So a couple clarifications first. I'm on leave from University of California, but I've been at Amazon for more than 2 years now, and looks like I'm staying at Amazon. It's a great place to be. I think the previous speaker put a hiring slide at the beginning of his talk, at the end of his talk. I don't have a hiring slide, so I'll just say at the beginning, yeah, we have positions available also in Seattle and Silicon Valley and other places. And yeah, I'm leading the Central Machine Learning Group in Seattle. We actually have a big new machine learning effort in AWS, and Alex Smoler joined Amazon recently, and he's leading that effort. He's based in Silicon Valley. So Amazon is really expanding and doing well in machine learning. What I'm going to talk about today is 4 different topics. I only have 30 minutes, so I won't be able to go into depth on them, especially not on the first 3. And these are representative problems, representative of the sort of problem that we face at Amazon. And we work on practical machine learning questions, but then the practical questions raise interesting theoretical questions, at least some of the time. And so I hope that what I say is going to be interesting. Everything in this talk, all the information is actually already public, so I'm bringing it together. I am going to give opinions. The opinions are mine. They're not Amazon's. And before I joined Amazon, I'd spent some time consulting for other companies, and I've had many students who've joined other companies in the tech industry, these ones in particular. And I wasn't surprised when I arrived at Amazon. Although there's idiosyncrasies about the problems we're facing, there's a lot of commonality with the problems that other companies are facing. So I think that whether you're a researcher or whether you're working at a company, that what I talk about, you'll think, oh yeah, we have problems like that also. Here are the 4 problems that I'm going to be talking about. And the theme is from practice to theory. Of course, the usual phrase is from theory to practice, and the usual idea is that, well, researchers work on theoretical questions, and then they come up with theoretical answers to the questions. And then maybe the same people or other people will take those theoretical answers and turn them into practical solutions. But in fact, if you look at the history of science, often engineering is what drives progress in science and not the other way around. And I think the same is often true in computer science and machine learning. When you start looking at a practical problem, then you get new research questions, you get new ideas for answering those questions, and it's the practice that drives the theory often. So I have 4 examples of the sort of problem that we face at Amazon and where we got interesting results by thinking about the practical questions. So first, I'll talk about detecting anomalies in streaming data. And I think I only have 30 minutes until 11 o'clock, but I'll try to cover all 4 of these. So a lot of organizations nowadays are generating a lot of streaming data. Internet of Things, if it's not generating petabytes of data now, will be soon. And Amazon is lucky to have a very successful cloud computing business. And one of the services that's provided by AWS is called Kinesis, and it's for ingesting streaming data. But something that I like to say, data is a cost, not a benefit. But that's one of the reasons why machine learning is so popular in industry nowadays, because big data actually it costs you money. It doesn't make you any money unless you do something with the data. And what you want to do with the data, that's essentially machine learning. You want to train predictive models. You want to use those models to take actions, make decisions. And it's no secret that a lot of streaming data services, well, they're good at ingesting the data, and they're good at putting the data somewhere where it's stored. But then what do you do with it? You've paid all this money just to ingest the data. So AWS is moving towards providing more value-added services on top of streaming data. And what we figured out, where we had an opportunity to do something interesting, was to provide anomaly detection on streaming data. And so we went from practice to theory. So we started with the practical question of, we have all these users and they want to do anomaly detection. But then there's hundreds of anomaly detection algorithms that have been published in the literature. and how can we possibly decide which one to implement and which one is going to be the most easy to use and general purpose for our users. So Nina Mishra is a principal researcher in our group, and fortunately she's an expert on streaming algorithms. And we collaborated with Sudipto Guha, who's professor at the University of Pennsylvania. We had a very good intern, Auki Shrivers from Stanford, and they systematically surveyed the landscape on anomaly detection algorithms, figured out what's the best starting point, and then what needs to be improved on this best starting point. And they had a paper at ICML this year, the robust random cut forest-based anomaly detection on streams. So definitely one of the themes from practice to theory is that you want to be pragmatic and you want to be eclectic in what methods you use. So we had no prior commitment to using random forests for doing anomaly detection. But by really looking at the literature and thinking from the point of view of a user, what's the best available algorithm for anomaly detection, the most robust, then it seemed to be a random forest algorithm. And then there were ways to improve it further, which is what they published in this ICML paper. Another connection between theory and practice is that, especially for something amorphous like anomaly detection, if you want users to trust your algorithm, it helps if they can know what the algorithm is in detail. You know, a lot of commercial software is ultimately black box. The users don't know what algorithm is implemented. But we didn't want to make it open source because we want the opportunity to continually improve it and to integrate it very closely with the rest of AWS Kinesis, which is not open source. But we did want to publish the algorithm so that people would know what it's doing, and then they can independently read this paper, evaluate whether it seems like it makes sense for them. And the algorithm specifically does have advantages compared to previous algorithms. So at the top is some synthetic data. It's simply a sine wave. And if you look in the middle, there's a small anomaly, and then there's a big anomaly where there's a disruption in the sine wave. And the red curve is the anomaly score provided by the algorithm. And indeed, you want an anomaly detection algorithm to react as quickly as possible. So this algorithm does react very quickly when there's the small anomaly. You can see the small red spike. And then it also reacts very quickly and with a strong reaction when there's a big anomaly, which comes just after the small anomaly. And there are other data sets where we can clearly show that other anomaly detection algorithms don't detect what's obviously an anomaly, and then this algorithm seems to be more robust in detecting a wider range of anomalies. And then, as an example of a real-world data set, so the bottom figure, the data is the blue curve, the blue time series, which is essentially the number of taxi trips hour by hour in New York City. So of course there's a lot of daily periodicity, there's a lot of weekly periodicity, and then there are anomalies which are caused by holidays. And yeah, it's always subjective what is an anomaly or not. So Christmas comes every year, so in that sense Christmas is just annual seasonality, it's not an anomaly. But if you look at things on the time frame of weeks, then Christmas is very much an anomaly. And this algorithm will detect things that are just very different from what would be normal. In particular, the New York City Marathon closed off a lot of streets, and that's very detectable as an anomaly. Christmas is detectable. A snowstorm in January is detectable. And the algorithm's not perfect. So Thanksgiving is different from other weeks also, and the algorithm doesn't detect that Thanksgiving is different. But you could argue that the difference in the pattern of taxi trips is, the difference is smaller at Thanksgiving than at these other strange events. No anomaly detection algorithm is going to be perfect. And that's one of the reasons why we wanted to publish the algorithm, so that people could really understand what it's doing when it's succeeding, and also occasionally when it's not succeeding. And So from theory to practice, this is now a released Amazon product. This is an article from a magazine for application developers. And so if you're a user of AWS, you can write SQL queries over your streaming data. And then there's a special operator you can put in your SQL queries, which is simply anomaly score. And so then you can set an alert, for example, whenever your data triggers an anomaly. And of course, we have a lot of plans for improving this. I can't really talk about those. That would be disclosing product plans. But we think this is an exciting opportunity for really helping people take advantage of Internet of Things. All right. Next topic I want to talk about briefly, actually very closely connected to the previous talk, which I really enjoyed. So at Amazon, like most large organizations nowadays, we love Spark. We use Spark a lot. And Amazon doesn't have a big tradition of contributing to open source software, but we certainly can. And we certainly want to be good citizens in the open source community and the research community. And at Amazon, we run a big website, and so we want to do a lot of real-time predictions. We want to be scoring users for what's the probability that the user will do this or do that. And so for some of that, we use Spark for training the models. And the previous talk, we heard a lot about improving the throughput of Spark, improving the flexibility of Spark, and the scalability. And that's great. But what we need also is to put models into production and then to have very low latency for individual test examples that are coming in that we need to make a prediction. And we found that Spark actually wasn't so good for this. And we evaluated Spark 1.6, Spark 2.0, Spark ML-lib, Spark ML. And we found actually very different numerical results for the different versions, but a consistent pattern that, so for actually what's a very small, by today's standards, predictive problem, using 20 newsgroups data sets, so a really tiny, tiny data set. We've done experiments with much, much bigger data sets. So the median latency for making a prediction for one test example was 30 milliseconds. And we care about the latency that is experienced by the unlucky customers that are experiencing particularly high latency. So here, I think if the P99 latency was 67 milliseconds, so even more unacceptable, because we want to often to render a web page, we're making dozens or hundreds of predictions just to make the decisions about exactly what's going to be displayed on one web page. And it turns out that Spark uses these rather heavyweight data structures. First it was RDDs, and then it was data frames, now it's data sets, and those impose a lot of overhead, about 5 milliseconds per operation in a pipeline. So I was very lucky to have a really smart PhD student intern this summer, Hussein Hazimeh, that's his picture. He's going to be a PhD student at MIT, actually he already is. And after delving into the internals of Spark, we realized that there was actually a very simple refactoring of the code that could get rid of a lot of the overhead. And so on this particular data set, the real-time predictions, rather than needing 31 milliseconds median, you can do 0.16 milliseconds median. And this is essentially by removing unnecessary work from the critical path of the software. But we learned something else about Spark. Spark is a victim of its own success. So the previous speaker talked about how there have been thousands of contributors. Well, it turns out that the core Spark team doesn't have the bandwidth to evaluate most pull requests. So we've submitted this as a pull request. This is a simple modification that I think could help a lot of people who are using Spark. And with almost no change, it applies to 1.6, 2.0, ML, ML-lib. And the status of the pull request is currently closed. And the reason ultimately is that the core developers of Spark, they just don't have the time to really think about and look at all the pull requests. And I'm sure there are other really good modifications, improvements to Spark also that are languishing out there. So if anyone's listening, just go and have a look at this pull request. All right. Third thing I want to talk about to give a flavor of how we think at Amazon is what's our most important algorithm for recommendations. So recommendations are pretty much the core of Amazon's business. And I see Ronnie Kohavi in the audience. He's going to know this. Amazon's been doing recommendations for at least 15 years. And there's one algorithm which is still the workhorse. And I want to explain why it's the workhorse. And there's a broader theme here of theory versus practice. So I spent many, many years as a professor of computer science. And I know that as researchers, we all pay lip service to simplicity. We all say, oh, yeah, simple is good. A simple algorithm, that's the holy grail. That's what we look for. But then you submit a paper for publication. It's got a simple algorithm. It's presented in a lucid way. It doesn't have pages and pages of mathematics. And your paper gets rejected. So in theory, researchers favor simplicity. In practice, they don't. There's also all this pressure for novelty. And if the simple idea has already been taken, then the only way to be novel is to make it more complicated. Now, in industry, simplicity genuinely wins. We're too busy to implement really complicated ideas correctly. And we really need low latency. And so let's think about recommender systems for a minute. So what do we want from a recommendation system? And, as a researcher, you might say, well, we want highly accurate recommendations. But it's not even really well defined what's an accurate recommendation. The customer might accept the recommendation, but then if they accept the recommendation and they buy a product and they don't like the product, then that's bad for Amazon in the long term. So really not totally clear what accuracy even means for recommendations. And I could go on about that. But here are 4 criteria that definitely we want for recommendations. We want to respect the privacy of the users. We don't want to be creepy. We will use personal information, but we don't want to use personal information in a way that makes any user unhappy with us or embarrassed. And then we want to make the recommendations understandable. People are going to be more likely to accept a recommendation if it doesn't come from left field, if it has an explanation, or if it seems plausible. Oh, yeah, I understand. Yeah, I do want that. Yeah, let me buy that. Then we want to make the recommendations responsive to a user's most recent interests. In general, I might be interested in buying a new sports car. But right now, I'm not thinking about sports cars. Right now, I might just be thinking about toothpaste. I run out of toothpaste. I need to buy some toothpaste. So I'm complicated. I'm a human. I'm interested in many different things. And the recommendations you show me should be relevant to what I'm interested in right now. And then we want low latency. Every company that operates a large website has done the experiments and knows that faster responsiveness on the website leads to greater user satisfaction, leads to greater revenue. It's better in every way. So you put together these 4 requirements, and most of the research on recommendation systems is irrelevant. It's too complicated and doesn't address these basic requirements. So what is the most important recommendation algorithm? So at Amazon, we like to be transparent with the users. And so if we have a headline that describes an algorithm, that headline is essentially the English description of the algorithm. Customers who viewed this item also viewed. So this is just historical data. If I'm looking at a web page and showing a piece of jewelry, then we have data for everybody who looked at this web page with this piece of jewelry. What are the other things that they looked at in the same session or in the same day? And this is a conditional probability. So essentially what we're doing for recommendations is we're showing other items that have the highest probability in the historical data conditioned on the item that the customer is looking at now. And of course, we do have a lot of other recommendation algorithms, some of which are more sophisticated, some of which are addressing more complicated scenarios, but this is the most important algorithm. This is the one that is showing recommendations on almost every web page on the Amazon website. And it's a wonderful algorithm because it's so simple and because it meets these requirements. It's respecting the privacy of the users. It's not using the history of the user. It's just using what's the user looking at right now. So that's number 3. It's responsive to the user's most recent interests. What's he looking at right now? It's understandable. The algorithm's understandable. Customers who viewed this also viewed, and then there's usually a logical relationship between the items that are being displayed, recommended. They're substitutes or they're complements. And then essentially it's a table lookup and a key value store. So very easy to generate with millisecond latency. All right, so those were the 3 topics that I wanted to mention briefly and go into a bit more detail about Uplift. So this is also something that's well known in some of the research community, but I think underappreciated. So there was one of the talks that I really liked from Yahoo this morning was about finding target users for advertising a particular type of product. And this is what we mostly do at Amazon and what I think every similar company mostly does. So we build response models. So if X is a user and there's some binary response R, so the response could be that the user buys shoes over some time period, say the next 2 weeks. And so R equals 1 means the user responds, R equals 0 means they don't respond. And so we train models to predict the probability of response. And then we send messages and coupons to the users that have a high response probability. So this is the bread and butter of supervised learning for advertising. But if you think about it, this is not good logic. If you send a 20% coupon to somebody who is going to buy the product anyhow, then you, the company, you just lost that 20%. They were going to buy it anyhow. Why did you give them a discount? Now, actually, at Amazon, we're very customer-centric, and if we give one person a 20% discount, we want that 20% discount to be available to everyone because we don't want to do price discrimination. But in general, the logic still applies. What you really care about is not correlation, but causation. You do want to send the advertisement to somebody if it tips them over the edge to make them buy the product. If they were going to buy the product anyhow, then don't bother to send them the advertisement. So the issue is not whether the advertisement is correlated with buying the product. The issue is whether the advertisement is causal for buying the product. So that's what I have on this slide. So response probability, is it actually useful? Well, in principle, no. Another way of putting it is that our goal is not to predict the future. People often think, machine learning is about making predictions. Well, I don't agree. Machine learning is about selecting actions and making decisions. And then the predictions are inputs into the decision-making algorithm, which usually is a utility maximization economic algorithm. So just predicting the behavior of users is of limited interest. What we really want to do is we have a set of treatments, and we want to choose the treatment that influences the user the most in the direction that we want to influence the user. So if you think of, you have a set of treatments, so capital T would be the random variable for which treatment, lowercase t would be one of the different available treatments, and then for each available treatment, we want to compute the probability of response given that treatment for this particular user. And then for each x, we want to choose the t for that x that gives the highest probability. And there's a strong risk in ignoring this issue that the same treatment can be beneficial for some users and neutral for other users, maybe even harmful for other users. So this is a figure that I got from Nicholas Radcliffe, who's some researcher who studied this. So I think this is a picture of churn probability. So the brown and the green curves are just two different models that are estimating the same thing, which is the probability that a user is going to churn, that the user is going to stop using the service. And the users have been ranked by this probability. So the 5% of users that are the most likely to churn, their churn probability is almost 50%. And so these are the users that you'd really like to target and give them some treatment that will induce them to not churn. And then the blue dashed line is the probability of maybe this, so probably abstain, but the blue dashed line is the probability of response given a treatment. And if you look at the 5% of users who have the highest probability, the treatment is actually harmful. It's the other users for which the treatment is slightly beneficial. So this is quite well known in medicine, and it certainly happens in marketing also. You can have a treatment which is beneficial for one subset of users and harmful for another subset of users. And then the treatment may even appear to be beneficial on average over all users. But it's still a mistake to administer the treatment to all users. You only want to administer it to the subset for whom it actually is beneficial. So this treatment has a negative effect for users in the top 5%. And outside the internet industry, people know this very, very well. Anybody recognize who's in the picture? Is he in the audience? Rayed, are you in the audience? That's Rayed Ghani. Rayed's a great machine learning researcher, and he was chief scientist for President Obama's re-election campaign in 2012. And so pretty much everything we know about data-driven marketing, they used in the Obama campaign. And of course, politicians everywhere know that if you're a Republican, you don't bother trying to send messages to Democrats. You're not going to change their mind. The message will be neutral at best, and it might even be negative from the point of view of the Republican if it reminds the Democrat that there's an election, and then it makes the Democrat want to go and vote, and vice versa, of course. So you want to send persuasive messages to the people you can influence, the undecided ones, and different messages to different users. If you have somebody who's going to vote for you anyhow, well, you send messages to them to ask them to donate money, or you send messages to them to remind them to go and vote. You don't bother trying to persuade them because they're already persuaded. So let me spend 5 minutes talking about a particular data set that illustrates this. And there's a controversy in the research literature. So I think everybody accepts the logic of uplift. Everybody accepts the logic of causation. But the controversy is over whether it's actually possible in practice, whether it's easy to put this into practice, and how important the phenomenon is in typical marketing situations. And so we have a lot of data sets where uplift is important at Amazon, and we're taking into account this logic, but maybe not as much as we should. And so I wanted to take a small public data set and see whether how well the logic works in practice on the small data set. And if it works on this very small data set, then chances are it'll work even better on the sort of big data sets that we have internally. So the situation here is that the alternative treatments are different types of email advertisement, including no advertisement. So the question is, which advertisement should you send to which customer? The data set comes from consulting work by Kevin Hillstrom. It was published a few years ago. It's really tiny. It's just 64,000 customers of an e-commerce site. And then these customers were randomized to 3 treatments. One treatment was no advertising. Another treatment was advertising men's clothing. And the third treatment was advertising women's clothing. And so the question is, for a given customer, which treatment is the most effective? There are 3 outcomes. This is something that comes up immediately in practice that isn't taken into account much in theory. So in practice, almost every data set, every prediction problem, we have multiple outcomes. Here, one outcome is, do they visit the website? A different outcome is, do they buy something? And then another third outcome is how much do they spend? And ultimately, we're interested in maximizing total revenue. If you look at the data, then it seems that the email treatment has a bigger influence on whether or not somebody visits than it does on whether or not they buy, given that they visit, or on how much they spend, given that they buy something. And this makes sense. They can click on the email and they can visit the website, but once they're on the website, then they've probably forgotten the email, and then they're going to behave in some normal way on the website. So we'll just analyze the causal influence of the different treatments for whether or not a user visits the website. I was talking before about the importance of simplicity in industry. So I'm going to use the simplest possible model for predicting probabilities. This is simpler than logistic regression. It's linear regression. And a lot of people may not realize that it actually is legitimate to use linear regression to predict probabilities. Linear regression is used quite a lot to predict probabilities by econometricians. It's not used a lot in machine learning, but there's actually no good theoretical reason to avoid it.
Robustness.
Robustness? Okay, I'd like to see the data about that, the evidence. I want to get those one. Good, good. So this is a very small data set, and most of our applications where we have large data sets, we're really interested in predictive accuracy. It is worth it to get the 1% more predictive accuracy. Also, we want fire and forget methods. We want really robust methods. But this is a data set that I was being old-fashioned about. I was doing sort of a hand analysis of it. So there were some types of robustness that weren't so important to me. So using the linear probability model, I do get predicted probabilities that are well calibrated because square loss is a proper loss. And then I have two treatment indicators. So one treatment indicator is just M, meaning they get the men's email. W, they get the women's email. So that'll be M equals 1 or W equals 1. And then M equals 0, W equals 0 would mean no email. And I don't have time to go into the details of analyzing the model. Even a linear regression model takes a little bit of time to walk somebody through the analysis. But what the model is essentially saying is that so the baseline probability of visiting the website is 7.5%. And then there are various influences like rural versus suburban versus urban. And then if somebody has bought men's clothing in the past and you send them the men's advertising email, then they have a 6.5% higher probability of visiting. So the men's email is highly influential if they've bought men's clothing in the past. But interestingly, the men's email is also highly influential if they've bought women's clothing in the past. That's a bit more surprising. And the women's email is highly influential if they've bought women's clothing in the past. Okay, not so surprising. And then the really interesting thing, which I highlighted in gray here, is that the women's email is not effective for customers who've previously purchased only men's clothing. So if you have a customer who's only purchased men's clothing, and you send that person an email advertising men's clothing, well, they're more likely to come and visit the website. But they've only purchased men's clothing, you send them an advertisement for women's clothing, no effect. Doesn't increase their probability of visiting. So this is, we didn't at all know to expect this before looking at the data. So a whole other question in theory versus practice is being data-driven versus being hypothesis-driven. So I certainly did not have this hypothesis before looking at the data. But it's a statistically significant finding. So the men's email is effective for anybody who's purchased men's or women's clothing before. The women's email is only effective for people who have purchased women's clothing before. And so we get an optimal treatment policy. And if somebody's only bought men's clothing, send them the men's email. If they've only bought women's clothing, you can send them either email. They're equally effective. If they've bought both men's and women's clothing before, so they're really great customers, then you send them the men's email. So you can actually simplify this down to send the men's email to every customer. And so this is really interesting conclusion, I think, for two reasons. One is that the conclusion we've arrived at is that we had three different treatments, but one of the treatments turns out to be best for every customer. And this is something that we see sometimes at Amazon. So we might have a whole range of different advertisements we can send, but then we find out that one advertisement is the best one for every customer. And so to implement that policy, you don't need any machine learning. You just send that advertisement to every customer. But you still needed to do machine learning and data analysis to figure out that is the best policy. It wasn't obviously the best policy in advance. And from this also, we get an interesting hypothesis that maybe we can use to think about designing new advertisements or further campaigns. So hypothesis is that women tend to buy clothing for their families, so both male and female clothing, whereas men tend to buy clothing only for themselves. So then we can go out and we could do some market research, and maybe we could interview customers. And one of the questions we'll want to ask them is, well, who do you buy clothing for? Your whole family, just people of the same gender as you, or only yourself? And because the data are suggesting hypotheses to investigate. To validate this insight, there's an alternative approach to the data. So we want to confirm, have we really found an optimal policy? There might be more than one optimal policy within statistical fluctuation, but have we found one? So the approach is, train a model of response for each treatment, and then for a user in a test set, you plot the predicted response probability for each different treatment. So here, just two different treatments. It makes it a two-dimensional plot. Probability of response given one treatment versus probability of response given the other treatment. And then we divide the test set into three parts. The users have previously purchased both men's and women's clothing, just one, just the other. And then for the people who have previously purchased just men's clothing or men's and women's clothing, then the probability of response with the men's treatment should be systematically higher than the probability of response with the women's treatment. And that's exactly what we do see. So this is results using random forests, so totally different modeling method from linear regression. And there's a lot of noise in the data, partly because it's such a small data set. But yeah, so the bottom two clouds are systematically above the diagonal line. So this says that the men's treatment is predicted to be more effective than the women's treatment for these two subsets of test examples. And then the cloud at the top is the customers who previously only bought women's clothing, and then the two models, the cloud of points is on the diagonal. So there's no systematic pattern about which treatment is more effective for this subset of customers. All right, I think my last slide, what comes next? So said the conclusion, one treatment can be optimal for all customers. And I love simple conclusions, much easier to just send the same email to every customer than to be using machine learning models in production, needing very low latency to make different decisions for different customers. Where we want to go next, after doing uplift modeling, is we want to do reinforcement learning, because for a given customer, we're actually interacting with them over time. We're showing them many recommendations. We're sending them many messages. We're taking other actions with respect to them. So we want to use reinforcement learning to optimize the whole sequence of actions over time with respect to each user. And so that means learning simultaneously how the customers evolve and how they respond to actions that we take. And a few minutes ago I said that applied machine learning is not fundamentally about making predictions. It's about choosing actions. And this is one of the reasons why I really like reinforcement learning, because reinforcement learning has this strong focus on actions as opposed to predictions. All right, I'll stop here.